So magnets exist as dipoles, and therefore we can actually consider this as one of the important facts for one of the laws that we are going to discuss today. So therefore we need to consider all the time that North Pole and South Pole exist together, and there are no like monopoles in existence as of now. And we also talked about the magnetomotive force in the last class. Magnetic force, which is defined by QV in cross V, where Q is the electric charge which is moving with a certain velocity V and under a certain magnetic field B. So this B is velocity, and this B is the magnetic flux density. So with this equation, we derived the direction of the magnetic force under the velocity and magnetic flux density of the magnetic field. So today we are going to use those concepts, and we are going to discuss about the laws which are related to the magnetic field. So we are going to talk about Gauss's law for magnetic field. Okay, so Gauss's law for magnetic field is very simple actually. You know, we learned about Gauss's law for the electric field. So when we talk about the Gauss's law for the magnetic field, a similar law is defined. In the Gauss's law for magnetic field, we are considering a situation where we are having a closed surface. This closed surface can have any shape. So inside this closed surface, we have some magnet or some magnetic field inducing source, and because of this magnet, some magnetic field lines are generated around this space, right, inside the closed surface and outside the closed surface, right? So in the last class, we drew the magnetic field lines around a bar magnet like this. Let's say this is a bar magnet. So the magnetic field lines that we can draw around this bar magnet will be symmetrical around its axis, and we can draw the field lines which will be continuous, and we can draw them like symmetrically around the axis. So once we come to the closed surface, I mean, I will erase the closed surface. I will draw that again in another color. Let's assume the closed surface is something like this. The magnetic field lines, since they are like symmetrically symmetrical around its axis, the total number of magnetic field lines which are going outwards equal to the total magnetic flux coming inward. So So this is the Gaussian surface. Right, so this is a closed surface. A closed surface. And these are the magnetic field lines. And these magnetic field lines are symmetrical, and once you take the like uh, net magnetic flux, which is going outward, you can find that it is equal to 0. So that is the Gaussian law. So so the Gaussian law says that the total magnetic flux through a closed surface is 0. That means that the total magnetic flux which is going out is equal to the total magnetic flux that is coming in. Okay, so do you have any question so far? So Gaussian law is very simple. The total magnetic flux which is going outward, right? I will write, yeah, magnetic flux going outward. I will have to write it in here, going outward. Outward through a closed surface is equal to 0. Um, so we can denote it mathematically, and we can denote it in two forms, the integral form and the differential form. So I will erase this. Are you writing? Is somebody writing? Can you hands up if you are writing? Right. So another thing is, if by any chance the monopoles exist, if monopoles exist, this law will not be true and it will have to be modified. So as of now, since monopoles are not existing, this law is correct. That means magnetic flux going outward from a Gaussian surface is equal to 0. So I will write the integral form and the differential forms of Gaussian law for the magnetic field. Okay, so the integral form is like this. So we have a closed integral, and for 0, right? So in here, the integral means closed surface. Okay, so I will write a letter A in here to indicate it is a closed surface. So this integral represents closed surface. So integration has to happen all over the closed surface area. So the integration has to happen all over the closed surface area. So the integration of magnetic flux density over the total surface area will be equal to 0. The total amount of magnetic flux that is going out will be 0. That is what is meant by this integration. So dA is the smallest surface area element of the closed surface. So we are taking a smallest area element of the closed surface that we are considering, and we are taking the perpendicular vector of that uh, area, which is known as dA vector, which is perpendicular to the surface, and then we are taking the magnetic flux, which is going in the same direction as the dA vector. So the magnetic flux can be in another direction. It doesn't have to be in the same direction as of dA vector. So we can have the magnetic flux in other directions. However, once we are taking the dot product, then only the component of B along the direction of dA vector is getting a certain scalar value. Other things are going to get cancelled out. So the total flux which is going outward from this closed surface can be found by taking the dot product between this magnetic flux density, which is giving us the magnetic flux across a small unit area, and then we are going to integrate it all over the total surface area. Then we can find the total flux which is going out, and that flux will be equal to 0 according to Gaussian law. Let's say, we don't have to say, I'm not going to complicate this. This is close. That's it. Right. So we are having multiple. So can have like magnetic flux in all directions. We are only taking the flux which is perpendicular to the surface, and then we are integrating it all over the surface, and the value will be equal to 0. So then we have the differential form. Differential form is divergence of B is equal to 0, right? Divergence of B is equal to 0. The divergence, that word itself means that the diverging ability of the magnetic flux is 0. Diverging means going out. So the total going out of the magnetic field is 0. So this is the differential form, right? So it also says that there's no at each point in the surface, we will say. There's no net magnetic flux which is going out at each point in the surface. At any point, let's say at any point. So basically that is the Gaussian law. I think it is very simple and we already can understand that kind of clearly. Do you have any questions? Is it okay if I erase this? Are you writing? So actually magnetomotive force is like the potential that is created by the magnetic field. Yeah, I mean, once you are adding some varying current across a certain coil, magnetomotive force is created. Yeah, flux is created. So it's like the electromotive force. There's some electromotive force which is equivalent to electric potential. Some, yeah. Similarly, we have for electromotive force, but the magnetic potential is not physically available. It's not like a voltage. It is like a flux, as you said, that is generating in a certain direction. We don't see any voltage. We can't make any voltage measurement, but field is created. Yeah, it is moving in a electric charge. When it is moving with some velocity uh, under a certain magnetic field, then a force is acting on that charge. That force is we call as magnetic force. Yeah. Sorry. Yes, actually, yeah, it is continuous. Yes. Yeah. The not perpendicular like components are not getting added because we are only considering the perpendicular vectors which are going out from the surface. Yeah, I mean the dot product. Once we take the dot product between the area vector and the area vector is perpendicular to the surface, only the magnetic flux which is along the area vector will get added. So the total magnetic flux is counted as the magnetic flux which is perpendicularly coming in and coming out, going out from the surface. For us to make it like, yeah, yeah, that is not considered as flux actually. We are defining flux as the like, I mean flux. We do have flux in a certain direction, but we actually in mathematically we are considering only the perpendicular components actually. Other components will not affect the kind of, yeah, it will not affect the magnetic field as much. It is going in a certain other direction, right? Only the perpendicular one will be the most strongest one. So yeah, so when the magnetic flux is going in another direction, its effect on our, our object or something is less, it's going in another direction. Right, so we are going to learn about the Faraday's law next. And the Faraday's law talks about the electromotive force that will be generated because of a changing magnetic flux. So changing magnetic field, right? Once we are changing some magnetic field across a certain metal loop, for example, a certain voltage is induced in that metal loop due to the magnetic field, right? So once we are changing the magnetic field across that loop, a certain voltage is created. However, we have to also consider something called the conservation of energy in the nature. That means like once some change is occurring in the nature, nature is trying to oppose that change. So once some magnetic flux is increased by somebody, then nature is trying to oppose that change that is brought into this environment suddenly. So nature is trying to oppose it, and they are going to create the electric potential, but in the opposite direction, right? So because of that, uh, we define the Faraday's law in a certain way. So I will first write the mathematical equations of the Faraday's law, and then I will write the definition of that law in word. So, so the integral form of the Faraday's law I will write first. So the electric field which we can integrate over a certain loop, like metal loop or something. In here I write L because I'm doing the integration over a line like a metal loop, metal conducting wire, something circular, not having surface, not a closed surface. So it is equal to the rate of change of magnetic flux that can be brought along certain surface that can be like, I will write it first and then I will explain. So there are different ways to write this law. So this is the integral form, right? So this shows that like this surface area shows like total magnetic flux that is coming out of a certain surface that we have determined in the space, right? This surface might not actually exist. It could be something virtual, but the total magnetic flux around that surface uh, is denoted by this integration. The total magnetic flux that is coming out of a certain surface area of A. So it could be, I mean, that area is a closed surface that we are considering. Okay, so I will explain again if you can't understand this. Yeah. Ah. It is a loop, right? We are considering some kind of a loop in here. So we are going to actually add some magnetic field across a certain loop in here. So we are only going to consider like one single loop for this example. It could be some multiple metal. Yeah. Uh, yes. So we are, yeah. So we are defining like a certain area across which this magnetic flux is generated, right? So this, let's say that this like magnetic field lines are generated out of a certain closed surface, right? So if I draw that surface, I think it's going to confuse. Like this is the loop, right? That as I said, that surface area is not, it is something we can consider as a like a closed surface, right? But even this drawing is wrong. It could be like generating from another place. Let's assume that the source of the magnetic flux is somewhere here, right? Out of that closed surface, the magnetic flux is generated due to a certain magnet or something, right? So let's assume this circle I have drawn is a sphere actually. It's a sphere. Inside this sphere, we have a certain magnet, north, south. Because of this magnet, we create some kind of a magnetic flux, right? So this circle area is what we denote as the area here. So it's actually is what happens is actually we are bringing a certain magnet near to this loop. We are adding some magnetic field to this loop, right? So I can also draw this in a more practical manner. Like we can actually consider that I'm bringing a certain like a magnet near here, north south, some magnet. I'm bringing it here, and then I'm adding that magnetic field over this closed loop. So this magnetic flux is created due to this magnet. So anyway, so after adding this magnetic flux to this loop, we can actually have some electromotive force generated in the loop. However, some due to the opposing nature of the uh, opposing act of the nature, we see that the potential is created in the opposite direction of opposite direction to the direction that we are expecting it to get produced due to this magnetic flux. So what happens is once we are adding this magnetic flux, the nature is like trying to oppose it. So the nature is creating an electric current in the opposite direction. So I will erase this one, right? So once we are adding this flux, the nature is like by the right hand rule, actually the current will be, I mean the electric field will be in this direction. Electric field will be in the in this direction. However, by the nature will oppose that action, because the nature will is seeing that this flux addition as a like a something that is abnormal or something that is done to imbalance the energy in the nature. So it is trying to reverse that action. So because of that, the nature is like, I mean, by nature, this current is generated in the opposite direction, opposing the flux change. And then because of this current, an opposing magnetic flux is generated, which is generated in the opposite direction. So, so the current which is generated is due to the electric potential that is generated, and that electric potential we call as electromotive force. So electric potential or voltage is generated in the opposite direction to the direction of the electric field that we can see forming once we are adding the magnetic field. So the electric potential or electromotive force is generated in the other direction, and therefore once we are increasing magnetic flux in a certain direction across a metal loop, then we can see the voltage increasing in the opposite direction. So because of that, we are seeing, in other words, voltage decreasing in the normal direction, or in the in this direction, right? In the what you call anti-clockwise direction. So this minus sign is added to show the exact the exact behavior of the magnitude of the electric potential. Electric potential is decreasing in the certain direction, means increasing in the other direction. So this minus sign is coming because of Lenz's law. And so inside Faraday's law, we have the combination or the support or the ideas of lens also included. So basically Faraday's law said that once we are changing the rate of magnetic flux across a certain metal loop, we can create some electric potential across that loop. So basically that was his theorem. So in addition to that, Lenz's law proposed the usage of minus sign in front of this expression uh, in order to show the direction of the electromotive force. So basically the integral law of Faraday's law will be like this. The differential form will be very like simple than this one, which will be curl of E will be minus dabba dabba B over dabba T. That means the rate of change of magnetic flux is is equal but in opposite direction to the amount of uh, electric potential that is created around the edge of this loop, right? So so now we are considering this loop, right? However, if for example you are considering a situation we are having some metal sheet or some kind of a material in between these loops, even then we only have the electric potential generated only in the outside or the boundary of this loop or the boundary of this surface sheet, right? So therefore, I mean, inside this surface, there could be some electric potentials generated, but all that is generated are cancelling out each other because of the curly nature of the electric potential. So the curl curls are going to cancel each other inside the surface. So you can search more on that as well. And because of that, only the electric potential that is generated or that is remaining at the boundaries will contribute to the potential that is created. Right. So this electric potential will be generated mainly because of the uh, generated uh, at the edge of the loop or edge of the surface. So that is why actually we are having the line integral. So even if we don't consider the loop for any kind of a scenario where we have a surface which is not closed, but a general surface, then the electric potential is seen to be forming around the edge of the surface. Right, so in here the curl of E. So the curl of E is equal to the rate of change of the magnetic flux across a certain surface or loop. So curl of E will give us the actually electric potential that will be generated. So basically, that's the idea of Faraday's law. Do you have questions? Yeah, electric potential. Yes. Yeah, it is a voltage. It is a voltage, and therefore, like the current is flowing in this direction. Now, the voltage is generated. For example, the high voltage is in this direction, and the low voltage is in this direction. Because of that, the current is flowing in this direction. A voltage is created, but like it's difficult to show in the metal loop. But in this direction, it's forming in this direction, in the opposite direction to the direction of electricity. Yes. Yeah, difference in the voltage means like once we differ the magnetic flux, the potential will differ. Do you have question? So if the magnetic flux is not varied, then we can't see any electric potential generating, right? So if magnetic flux is not varied with time, then the potential will be zero. Electric potential will be zero. All right. So next, we are going to talk about the magnetomotive force, and the magnetomotive force was defined by the Ampere's law, basically. The Ampere's law says the magnetomotive force around a closed path is equal to the total uh, charge, current, and the uh, uh, so I need to see the definition across the surface. We can say I will recheck this definition. You need to check this definition, right? So yeah. Mhm. Yeah, in here we are changing the electric flux. Yeah, yeah, the total, yeah, magnetomotive potential, magnetic potential that is created. So you are saying it is equal to the, um, yeah, in here we are actually considering uh, the B actually, B into ds. B, magnetic flux density into B. B is like, yeah, it is also related to mu naught into H, right? Yeah, yeah, that's in free space. So they are almost similar. So same effect will be there actually. Just different, define. Yeah. So yeah. So we we do have, like, so, for the SI units also we do have different units that we can define. However, I think just understanding how this works will be enough, and just understanding the basic, like the simple form, and understanding it visually will be more important, and you'll be able to understand any equation. Once you have the visual idea about what's happening, and you can understand any type of, any form of the same equation you can find. However, like the correct equations are given in the books, like you can find in like standard books the correct equations with the correct notation. So there are two forms for the Ampere's law: integral form and the differential form. So in integral form, we have B in here. Actually, I'm taking B into dl equals the I don't know whether you have you have considered this equation in your classes. Mu naught epsilon naught over rate of change of electric flux over the area. So actually, this part is not much available in the machines. In the machines only, I think mu naught I is available. Yeah, you are considering solenoids and the effects of solenoids and how they are working in machines. However, like once we are changing electric flux, like deliberately in our systems, we are changing electric flux because we want. So we are adding something additional to the equation. So this is I think the correct or the complete one, which considers everything, that every like situation that can happen. So if you are not changing electric field across that surface or a loop or something, we can consider this part as zero. So this part will not be there. However, once we actually consider all the scenarios, we need to have this complete equation to evaluate the the law or the behavior of our systems. So the integral form will be like this. So uh, it is also similar to the previous case. However, in here we have the rate of change of the electric flux, not the magnetic flux. Earlier we talked about the magnetic flux and how it is changing with the time. Right, so in here we are having a certain like a loop or some kind of a metal sheet, and across that we are changing the electric flux across that surface. So once we are changing the electric flux across that surface, also we are having like electric charges in this metal sheet, which can so once we are adding electric flux, the electric charges in this metal sheet also get activated, and the charges get they move from like from their location to another location. And because of that, once electric charges move inside this sheet, electric charge currents are produced in this surface. So electric charge currents are produced. So electric charge currents which are produced are known as is given as capital I in here. So given as capital I. So because of the total the current uh, which is available in the sheet and the electric flux which we are changing over time, a certain magnetomotive force is created around this loop. Right, so magnetomotive force that is created around this loop we can find out from this Ampere's law. It is given by this equation, and based on the rate of change of electric flux and the electric charge which is on the metal sheet that is given by this circle, the magnetic potential is generated. So the effect of both current and the electric flux rate is changed, taken into consideration in here when we are measuring when we are defining the magnetic potential. Earlier we only had the flux of magnetic flux only. Now the charge current is also changed. It also has a certain direction. Effect also comes, and therefore we are only adding those terms, and the current, that electric charge current that will be produced will form the signs in a correct way, such that the whatever the energy conservation is happening. Mm. Everything, yeah. Yes, yeah. You only had I in here. Mm-hmm. So you had Ni equals in here like this. Mm-hmm. 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 Yeah. Mu A is the area of the. Mm-hmm. Okay, so it is actually just a evolution of this equation. Yes. So yeah. Yes. So I think you can actually add like as you said, mu naught and so on, and find this primary equation. I think as, yeah, I think so. Hopefully this is the correct equation, right? So you can also refer from books and let me know if there's something wrong with this equation. Please let me know. I have also tried to find the most correct equation, right? So I think you can derive other types of equations from this one. That is why I think electric and magnetic fields were introduced before circuit theory. Before circuit theory, they were considering both, I mean, electric and magnetic fields and their effect on electric circuits. And they have simplified it, and they have found circuit theory and other kind of other equations that make us easy to do the, yeah, who are doing any type of like a high frequency, low frequency, any type of engineering tasks. So this is the integral form of the Ampere's law, and the differential form of the Ampere's law is basically the curl of B is going to be equal to the rate of uh, is also equal to the mu naught in here J, mu naught J, which means the current density. So in this curl B part, what we are doing is we are only considering one point. How the like curl of that magnetic field is changing, that and how it's affecting the current density, or how it is varying with the current density and the electric flux rate, or electric flux change. So in here mu naught epsilon naught dabba E over dabba T. So in here current density means earlier we took the symbol I. So I over surface area A will give us the J. That means the current density per unit area. In a unit area, how much of a current is available, and in that unit area, how the electric flux change, how that affects the curl of the magnetic flux in in the space in a certain area. So we can use the differential form to consider about unit spaces, unit area, unit length, unit volume, something like that. So integral form is finding the total magnetic flux based potential or electric potential created over the total surface. No, actually, positive and negative charges are there. So the current that we are considering is that how actually the charges are moving actually. So both charges are there. The direction of the charges moving I mean direction of the positive charges moving we define as the current, right? So yes, yes. So I think with that I'm going to end today's class. Do you have any questions?